Hello everyone, this is my first video talking about the Siemens SIMIT simulation platform software, and in the following months, I will use multiple videos to talk about this topic, Siemens SIMIT simulation platform. This is simulation and training system. I will use one drive application to explain and show how can we getting started with this SIMIT software. And this drive application, the vibration cancellation, this is one of my motivation to start learning and practicing this SIMIT software. In the following months, I will systematically introduce how can we use the SIMIT, how can we build up some simulation model to practice the simulated process object. I believe most of people will firstly ask me, what is the SIMIT software? What are useful for the simulation platform, right? So to explain this idea, I will go to this Siemens ID number 1097610007. This picture can give us a glance to explain how this SIMIT works for. As we know, in the real industry system, we have a PLC controller and the devices. We have the actuators, for example, the servo drives, VFD drives, or the motors. And then the actuators and the motors will be connected to the mechanical system to control the machines. So the machine we can understand as the mechanical system. So nowadays, one very popular word is named digital twins. We are trying to use the software to simulate the different levels of the hardware system. For example, from the Siemens side, when we try to simulate the controller, we will use PLCSim software or the PLCSim Advanced, the simulation software. And when we program the HMI, when we try to verify and validate some result from the HMI, we can use the HMI simulation software to run the simulation, right? This is a very simple way or daily used the simulation method. However, those simulation software, they can basically use for the PLC logic or data processing simulation. You can practice your logic or validate your calculation result. However, this is only the software. Your logic is not connecting the real world. So how can we simulate a real world devices? Then this SIMIT software is playing this role. For example, when we are using the VFD or servo drives, basically the servo drive or VFD, they are showing as the first order or second order transfer function behavior. So the Siemens provides some libraries as showing like here. It also provide some telegrams. So using those telegram and the function blocks in the SIMIT software, then the SIMIT can run as the virtual hardware actuator hardwares. For example, motors or VFD or servo drives. It also can communicate with the simulation controller. Till this level, the sensors and the actuators, the SIMIT can simulate those hardwares and communicate with the PLC, the simulation controller. Also, it can do a furthermore step. For example, if you are using the PLC control one heater exchanger or heater system or water level, some cases, the heater exchanger or water level system showing as the second order transfer function behavior. Then in the SIMIT software, you can program your process object as a second order transfer function in the SIMIT software. So your PLC can control a virtual process object to run inside this SIMIT software. To understand this SIMIT better, we can also go to this SIMIT menu. It named the SIMIT simulation platform. So these three items explain what is the SIMIT. It can complete a plant simulation, and also it can simulate the input and output for the testing signals for the controller. And also it can testing and commissioning automation software. Basically, the SIMIT playing the role at this level here. Other than the PLC and the HMI simulation, the SIMIT is mainly simulate actuator and sensors, as well as part of the process and the plant simulation roles. If you are the new learner, one website I highly recommend you can go is this. If you type in the support.industry.siemens.com, and then you can search the ID number here, 109746 429. And there you can jump to this web page. So this web page basically includes all the important information for learning SIMIT, as well as tons of application examples and manuals. For example, the manuals I just opened that come from here, SIMIT simulation platform. Okay, the latest version of the SIMIT, that's version 11. So this is the manual I'm opening. Then the second question people will ask, how can I learn this software? Does the software need a license? The answer is yes, but don't worry. The SIMIT software, especially from the 11 version, when you install the SIMIT software, it default also install the demo version. In the SIMIT demo mode, it can provide you the maximum of 30 input and output signals. And also in each input and output, you cannot greater than 30 bytes. Honestly, the 30 bytes is slightly low. A lot of applications will be limited by the 30 bytes rather than the 30 inputs and outputs, especially when you are going to use this SIMIT software to simulate analog signals, because one analog signals basically take 2 bytes. So 30 bytes is mainly the restrictions. But good things, the demo mode does not need any license. You can just install the SIMIT, the version 11, and practice this software. Then if we go to this 1.5, you will see this is software, the overall picture. So this software includes a bunch of function blocks, so allows this software can run the process object. Also, this software, you can draw the pictures. So this software can really run as a plant running there. Behind those graphs, it actually bunch of code behind. So if we scroll down, the typical code style is running as this chart style like this. So as we can see here, this is the multiply. So this is interface. This allows this analog signal can transfer to the PLC. And more importantly, some high-end the calculation function block we can use from this software library. For example, this is the integral. Integral is very common used function block from this software. For example, when we simulate a water level going up and going down, when we feed water into a tank. So the tank going up and going down basically come from this integral function block we can use. Other than this, it also have a bunch of function blocks. Especially my motivation to learn this software, I start from the drive system. I was trying to use this software to simulate a servo drive, Siemens Dynamics S120, and a simple level of a mass, the simple load system, so I can practice the vibration canceling. So this is the one key application I'm going to show in this video. Okay, for more details, I highly recommend you go back to this web page and also read the detail in this manual. This manual has about 1,000 pages. It includes a lot of information. Okay, let's go to our main meal. So in this video, I will use this software to practice one application that comes from the Siemens support website. It named this Dynamics VibX. So this application is used to simulate a load cancellation when we use the positioning control. And there's one solution provided from Siemens. The function block can reduce the load oscillation. It's very useful. But when we practice this load oscillation, the first question will be, where's my drive? Where's my load, right? This application provides a simple TI portal project and a SIMIT example project. In the TI portal project, it basically set up two kinds of positioning control, servo drive, and TO, technology object system. And the drive is using Dynamics S120, the servo drive system. And more importantly, in the SIMIT software, this example project, it provides you the load system. So like showing in this picture here. So this SIMIT example project considered the momentary of inertia from the motor and the load. It also considered the torque of the motor and speed of the motor, as well as the oscillation frequency. So this is our main meal in this video. I will use this application as a base. I like to use this application to show how can we practice this TI Portal Plus SIMIT demo system using this example project. Okay, let's start. So once we download these two example projects, I copy them at here. This is my SIMIT practice system. As I remember, the SIMIT version 11 software does not support the Windows Pro system. That's why I specially installed this virtual machine system, that is the Windows 10 Enterprise. And also I installed the TI Portal version 17. And once you install the SIMIT version 11, you will see it includes couple icons at here. So we will use this SIMIT demo. This demo does not need a license, but as I talked, so it has the 30 inputs and output limitation, as well as the 30 bytes from input and output for each. And also we need to install the Siemens PLCSim Advanced software, the version 4.0 SP1. So you need to install those important softwares, TI Portal version 17 and PLCSim and SIMIT version 11. Okay, and all the SIMIT version 11 project locate at this directory. Keep in mind, if you are using the SIMIT demo, this software, all your SIMIT project has to locate at this folder, this directory. You cannot locate your project in other folders. This is a limitation. Okay. Now let me show how can we retrieve all those example projects for our use. Okay. So firstly, I will open the TI Portal version 17 software. Let me retrieve this example project. Click this open existing project and click this browse and find out this compressed project. Okay, this is the example project we download and click open. And then the system will ask us which folder we can retrieve this project. And then the system will ask us which directory we will retrieve this project. So I will retrieve this project under here. So I will create one folder and named this vibration cancellation. Okay. All right, we open this project. So let's go to this project wheel. Okay, this CPU is a 1517 TF. T means this is the motion controller. F, this is the safety integrated controller. Okay, this is a very high-end controller. And in this project, we can see this is the vibration cancellation function here. You can read more details from the menu from this application, this example. And in this project, it also has the linear axis and the rotary axis. These two axes provide two scenarios. I will explain after. And from this technology object here, we can see the linear axis is here. And the rotary axis, it shows rotary axis drive and the rotary axis load. Okay, and from this hardware configuration, this is the motion controller, 1500 motion controller. And also it has a Siemens servo drive, Dynamics S120. Okay, and if we open this Dynamics S120, we can see this drive control unit is linked with 3 servo drive system. This is the drive axis 1 and the drive axis 2. This associated with here. So the drive axis 1 is connected with this TO, rotary axis, and the drive axis 2 is connected with this rotary axis load. These two drives play the role as one is the motor, one is the load. And there's also one linear axis here. The linear axis associated with here. This is the TO for the linear axis. Okay. And this is the linear axis is a little bit special to show the motor and the load. It actually includes 2 encoders behind. If we go to this configuration, and when we go to the drive, we can see here, this is the diagram for the servo drive and the motor. And especially when we click the encoder, we will see in this TO here is using two encoders. One encoder, this is cyclic absolute encoder. And one encoder, the encoder 2, that's an incremental encoder. This represents, if we go to the mechanic system, that means the encoder 1 is mounted at the motor side. But the encoder 2, it actually represents the load side position for the linear axis. Okay, that's why the system has two encoders configured. And because it's using the two encoders configuration, that's why when we use this axis for the positioning control to read two encoders, so for the Siemens side, we will use the telegram 106. If we go to here, the data exchange with drive, so the telegram we will use, this is standard telegram 106. The 105 and the 106 are common used telegram when we use the Siemens Servo drive for the positioning control. The 105 is a common used telegram. However, 105 only includes one encoder. If we are using two encoders, one comes from the servo end, one comes from the load side, then we will use the standard telegram 106. That's why this example system is using the standard telegram 106. Okay, but for the rotary axis, if we go to the configuration here, so the rotary axis, that encoder is configured only one encoder. Then for the data exchanging here is using the telegram 105. But this rotary axis, it also includes another rotary axis load here. So this axis plays the role as the load side. For example, some cases you will see to simulate a drive, the motor and the load. Basically, we can connect two motors together. One motor plays the role as a load. This is exactly that case here. And we will also see this interconnection at here. But in this case, we will mainly use this linear axis. I will explain why. Because when we use the SIMIT demo, it has 30 bytes limitation. So it doesn't allow us to use two axes because there are so many IOs need to communicate between the PLC and the drives. So it doesn't allow us to do two axes. So only one axis available. That's why we will mainly use the linear axis. So again, this linear axis is very typical. It has two encoders, this application example. It also has this torque. So this torque is actually using the standard telegram 750. Okay, so if we go to the drive again to have a global view, so go to the drive, Dynamics S120 drive. When we click this CU, this control unit, when we go to the telegram configuration, we will see this is the entire telegram here. And as we can see, the axis 1 and the axis 2, they are all rotary axis. So they are using the 105 and the 750 for the torque. And for the linear axis here is using 106 and the 750 for the torque. And also we can see this words. So for the input, it totally 16 words. It actually 32 bytes. For the output, it has 14 words. It's within 30 bytes. Then there's one question. For this input feedback from the drive to the controller system, it has 16 words, 32 bytes. It's greater than 30 bytes. It definitely has a trouble when we use this example. So I will show an alternative way to modify something to allow us to use this example. Okay? So this is the drive system. And then let's open the SIMIT system. Okay? So this is the TI Portal project. And this file, this is the SIMIT archived project. Okay? So we will use the SIMIT to open this archived project. So let's firstly open this SIMIT demo. Okay, once we open this SIMIT demo, let's click this retrieve to retrieve this compressed file to a project. Okay, so let's browse the compressed file. So let's browse that compressed file. Okay, this file is here. This is the one compressed file. We will see this is SIMIT archived this compressed file. Okay, let's click open. So you better create one shortcut on your desktop to directly browse this folder. Because for the SIMIT demo, this project, we have to unzip and create the project under this directory. You cannot create the project at other directory. Okay, then let's click this retrieve. Okay, it's very quick. After we retrieve, let's quickly browse what it has. So firstly, this SIMIT project is simulate the drive system. So this Perfect Drive 2, this represent the Dynamics S120, the server drive system. It has all the important telegrams here. It also has the encoder simulation component here. And if you recall, for the linear access, it has two encoders. That's why here it has two encoder simulations here. And to process the torque, to simulate the drive torque, so it also has this 750 torque, this function block at here. Okay. If we go to the rotor axis, the rotor axis is using the telegram 105. So this is actually for the telegram 105, the typical structure. It also has this Perfect Drive 750, the torque, this component. Okay, then go to the load. The load, this is very simple and very typical. This is for the telegram 105. Okay, then let's focus on this linear axis here. So if we go to this linear axis mechanics here, so we will see it has this speed control and this load system. This speed control, you can understand this as a simulation motor. So when we control this motor a speed command, then the motor will output a torque, the new meter unit, this result. And then this motor new meter torque result will be connected to here. This is a load system. If we open up the here, so this load represent motor connect one load. In this function block, it has the momentary of inertia setting from this parameter and also the load momentary of inertia. You can set them here. Okay, those are default value. It can simulate one motor connect one load. This load has a similar behavior as the drive motor. But in the real case, you can adjust this load, especially some cases, your load may be much higher than the motor. Then your system has a bigger or stronger momentary of inertia. So if this system has a stronger momentary of inertia, when the speed is doing acceleration or deceleration, you definitely need a high torque to control this load. So based on those parameters, the system will automatically calculate those vibration frequency. So the system will automatically calculate, especially this frequent for the resonance. The reason why the system has oscillation, that's because when your drive system and your load system, their frequency, they are similar. Especially when your drive system approach to the resonance of your load frequency, then the system will show the vibration. We will see the calculation result at here. Well, it is online. So this function block is mainly used to simulate two mass system, the real load, the load, that behavior. So the input, this is the motor torque. The output, this is the motor and the load speed and the degrees of the rotary. This is the motor, this is the load. If we hang up this, and if we review here, we will see those green that represent the signal communicate with the PLC. So the green signal come from the PLC command. We will see this STW and all those commands actually come from the telegram 106. And then the drive system receive the command, and eventually the drive will control the speed to the drive, to the motor. And eventually this drive system will control the motor, give a speed command. right? Then we will see this N-set linear will be connected to here, this N-set linear. This is the motor model. The drive give a command, speed command to this motor. And the motor connect to the load. And the load feedback, because the encoder connect to here, we have the second encoder, right? Then the second encoder, we will see this X actual linear will be connect to here, connect to the encoder here. But for the load degree will be connect to here. So basically, those are represent the encoder, the degree feedback go to this encoder input. Then the encoder using this function block to simulate this encoder, the encoder value is also using the telegram behind connect to the drive going back. Okay, and eventually all those encoder value will transfer to the PLC using the telegram 106. Okay, all right, this is the entire structure, and this three function block basically represent a drive and a motor and a load. This is system. Okay, so in this case we will mainly use this linear axis, and the key reason I have to use this way, that's because the limitation of this simulation software system. So if we go to here, this area named coupling, this area is used to connect the PLC, tell the simulation system so which kind of controller is using. So at here we will see all those interfaces represent the PLC, and the 30 variables actually that represent how many variables are being used at here. For example, if we go to the drive, all those green and red, those variables are connecting with the PLC, and the variable which is being used here will be counted as one tag in the SIMIT demo system. And if this variable is a word or the word, it actually taking 2 bytes or 4 bytes behind. If your PLC has a bunch of variables, but those variables are not being used in the program, which is fine, they will not count as the variables. As long as you are using those variables, then those variables will be counted as the variable number. Okay? So at here, as we can see, go back to here, all those variables, basically they all used in this SIMIT program here. So in this case, I'm gonna delete the rotary axis and the rotor axis load. Okay? Because of this limitation, the 30 variables and the bytes limitation, I have to delete part of this. So I will only use the linear axis as an example. Okay, delete. So only left is this linear axis. This telegram 106 has 2 encoders, this application. And also I will delete this rotor axis mechanics. Only left this linear one. Okay, now in this case, I only use one drive, those input and output. And if you recall, when I count the bytes numbers, actually those inputs, 32 bytes, is greater than 30. How can we do that? Here, there's one tricky thing. Firstly, let's review the TI portal. If we go to this TI portal, this axis here, if we open this configuration, click this encoder. This linear axis is using 2 encoders here. So the first encoder, that is a cyclic absolute. The second encoder, that's incremental. If we go to here, data exchange with encoder. So we can see the first encoder, it has this GX, ST, ST1, and 2. Each of this one, this XI, ST, they are one word. So it has 2 words here. This is the interface to read the encoder value. So that means for this encoder 1, it using the T1 and the T2, these 2 interfaces here. Each one, they are one word. Then let's shift to the encoder 2. So we will see the encoder 2 is using one incremental encoder, and here the system it actually only use the T1. this one word. The eXtinction is actually not using that. So basically we can save one word. So we can go back to the SIMIT here. Okay, so that eXtinction actually is at here. We can delete. But before I delete, I can directly click this start. Then the system will show some arrows. So we will see the arrows. One of the key arrows, the system will show the numbers of the byte here. Too many coupling signals used in the project. This is the arrow. That's because we are using 32 bytes, the signal transfer from the model to the PLC. Okay, we have to delete this one. So because the system is not using that, so we can delete. Okay, click the delete. We delete that. Now we can save. Okay, if now I quickly click this start simulate. So firstly, we can see this notice. So this is the SIMIT demo system. For this demo system, the runtime of a simulation is limited to 45 minutes, which is fine. And also it has the 30 bytes limitation. So if I close this, if every time I click this PLC, so it will show this sticker here. This is 30 bytes and 30 inputs and output for each, the limitation. Okay, so once we delete this eXtinction, then we can click this start to have a quick view if the system allows us to simulate. Because if you have a bunch of input and output, even you do this project very nice, but you cannot use this SIMIT demo project to simulate your model, right? It just wastes time. So we have to click this start to verify if your simulation system is lower than 30 bytes. So once you see the system showing this orange here, this yellow or orange, that means it's passed the compile and it started the simulation. That means, okay, now all the variables are below the 30 and below 30 bytes. Okay, so we can click this stop. So this is a very quick start just for testing purpose. Okay, let's close this stop. Okay, again, so in here, the system, we are only using the linear axis. So we only configure the linear axis. So go back to the TI Portal project. The TI Portal project, it has everything. We do not need to delete the rotor axis in the TI Portal side. So it doesn't matter. We are only use the linear axis as a simulation object. Okay, now we can compile this TI Portal project just to make sure if we change something. Okay, so we compile and save. And once you compile the TI Portal project, let's go back to here. Then we need to set up this coupling. So the PLC coupling setup here, that comes from the example project. Okay, however, it has everything like this. So I will recommend you delete this one and import your project again. Because some cases, once your TI Portal got recompiled or got some changes, then this interface, it will have some errors when you do the simulation. Especially this coupling area is used to connect the PLCSim advanced software. Okay, so we better delete here. Okay, don't worry, all those variables, they all the name. As long as all those variables name in the TI Portal side not changed, so once we import the TI Portal project again, they will connect and match together. So no worries about this. So now let's click this new coupling. Okay, and this is the place to set the coupling. Basically, coupling means it's used to allow the SIMIT software to connect something. So in this case, I'm using the PLCSim advanced. Okay, the PLCSim, this is the traditional PLCSim software. If you are using the i7-300 and i7-400 controller, then you have to use the PLCSim. But if you are using the S7-1500 controller, then you have to use the PLCSim Advanced to simulate. Okay, so now let's click OK. And in the meantime, the system will pop up this. So it's asking us to import the TI Portal project. So I'm using the TI Portal version 17. The version 17 allows us to import the TI Portal project at this SIMIT software here, while the TI Portal, this project still opening. So you do not need to close this TI Portal project. This is the project I'm opening at here. This is this TI Portal project. Okay, so I can click this TI Portal project and click the open. And then the system will import this TI Portal IOs. Okay, once it shows like this, don't forget, click this import. Okay, import here. So once we open this PLC, we can double check the variables. As we can see here, the default, they are Germany style, but now they are showing input and IW showing like this because I re-import my project. Okay, so we can see it has this linear axis and the rotary axis. We can see this rotary axis and linear axis. Again, so even all those variables are imported here, but because we delete all the rotary axis in the SIMIT project here, they are not being used. So they will not count as the variable numbers. Okay, don't worry. For the linear axis, we are using those linear axis variables. That's why those variables will be counted as a bytes and variable numbers. Okay, so this is input. And for the output here, same idea. For the linear axis input and output, we are using those variables. Okay, so when you try to import this TI Portal, some cases you will have error, like showing on the screen. Especially if this is the first time for you to use this software, you will have this error 100%. But don't worry, if you have this trouble, then you can search Computer Manager, Computer Management, and then find out the local user. Okay, so find out the username you are using. For example, in my case, I'm using this admin as my user. Okay, and then click the properties and find out this members of here. The key idea, your user must be the numbers of Siemens TIA openings. Okay, to add this Siemens TIA openings, you can click this add and then click this advanced and then click this find now. Then you will find this Siemens TIA openings. Okay, and click OK. Add this Siemens TIA openings, so allows your username as a number of this Siemens TIA openings, and click OK. And then you better restart your system, and then you can try. Next time when you import the TI Portal project, the system will not show the error anymore. Okay, so this is the limitation for this I/O. So once we import the TI Portal project at this coupling here, then basically this SIMIT project knows your PLC configuration behind. And now we can click the start and see what will happen. The system will pop up this error, this asynchronized setting. This asynchronized setting basically is used to the motion control synchronization mode. But for this case, because we are using the SIMIT demo, most likely the SIMIT demo doesn't support this asynchronized mode. So we can go to the project manager and turn off this mode. Ideally, we should use this mode. However, this SIMIT demo has a limitation. So we have to switch to the unsynchronized mode. Okay, so switch to here. Then save. And now we can start again. So let's see what will be once we click the start. See if this simulation can be started. So this time we will see this SIMIT switch to this orange, this yellow style. That means now this simulation system is started. And if we go to here, if we go to this drive and this load simulation here, if we click this 1, 2, 3, this means we will show the input output. As we can see here, it has some value here. That means this simulation system is running. If we go to this mechanic here and click this reading, we will see it has some values here. Okay, so this SIMIT system is running. Now we can shift to the TI portal side and let's start the PLC. Here is a question. So when we click the start, so behind what it's doing. So actually when we click the starting, once we set up this coupling, the SIMIT will automatically start the PLCSim advanced software. So if I minimize this software here, this is the TI portal. If I minimize the TI portal, let me open this PLC advanced software. Double click. So we will see when we start this SIMIT software, behind it actually create one instant at here. This instant named the SIMIT PLC. This is automatically created. This is actually answer one of my questions when I try to learn this SIMIT and the TI portal. My first question is, how can I set up the connection between the PLCSim Advanced, this software, this instant PLC, to the SIMIT software? Where can I set up the IP address, right? So this is a very common question. It's similar like how can we set up the connection between the PLC and the HMI? So for example, when we click this distribution here, it's showing the host ID and this communication interface. But actually, it's very easy because when we start this SIMIT, it automatically start up this instant PLC here. Then, once we use the TI portal download the PLC, we will download to this PLC here. Okay, and the reason why it created the PLC with IP address 192.168.0.1, that's because when we import the TI portal project to the SIMIT, the IP information from this TI portal project, it includes the IP address information. That's 192.168.0.1. It includes this IP address info. That's why when the SIMIT start up, so the SIMIT will automatically create one instant simulation PLC with this IP address. Okay, this is basically automatic, so we do not need to worry about this. So just to let you know, when we click the start, it automatically start up this PLC advanced software. And keep in mind, because I'm using this version 11, this SIMIT software, so this version 11 compatible with the PLCSim Advanced version 4.0 SP1. Keep in mind, you have to install the SP1. Okay, now to allow this SIMIT to find out the PLC, now we will download the TI portal project. So compile and download. Okay, this will be the similar idea as operating the real controller. So select the PEIE, we will use this interface, 0.1, right? And click the start search. So it actually searching all the interfaces behind. And because this PLCSim advanced software is opening, this interfaces created here. That's why the system can automatically search this PLCSim here. Okay, and now let's click this load. Okay, this is version 17 TI portal. This is the new feature. It's asking us consider this controller as a trusted controller. Okay, no problem. Consider as a trusted. And in the meantime, we will see the status of this simulation PLC here. So let's click the load. Okay, let's select this start module. And let's watch this status here. Okay, it's starting. That means we are downloading this controller. It's here. So now this controller is at the running mode. So now if I click this online, okay, once we click this go online, we will see this controller out here shows green. And here, I like to mention one thing. So from this network view, we will see this Dynamics S120 drive is showing disconnected. It actually doesn't matter. That's because the simulation software, when we connect here, so if we connect here, so all those interfaces that represent the telegrams, as long as all those telegrams input and output, IW, ID, right? All the input and output for the PLC. As long as all those input and output, they are communicating, we will see they are all communicating here. As long as they are communicating, then the PLC can control the signal and also read the signal to the input and output. So it actually doesn't matter if this controller can find a real this control unit of the drive. It doesn't matter. As long as all those input and output from the drive is communicating, then the PLC actually can control something and also can read something where those input and output. Okay, this ICOM status, it doesn't matter. Okay, don't worry about this. Okay, and now if we scroll down, if we open this linear axis, if we go to the commissioning here, so we will see there's no error, which is good. So if you have an error, you can try to click this confirm. Okay, and also I like to show one thing. If you are using one real device, so at here, if you click this active, then you can use this control panel to control the drive directly. Okay, so as we can see here, if I click this active, and now I can enable this access, and I can move this axis. Okay, I can stop. I can jog this axis. So that means this TO is connecting this drive system and using the input and output is operating this drive now. So which is very good, right? Even the connection, the network shows disconnect. But behind where the input and output, they are communicating behind. Okay. All right. This is also a great indication to show. So now we can use this TO to operate this simulated drive system. So while we are active this drive, while we are moving this axis, it actually operating this simulated drive system now. So if I click the jog, so I'm moving this way. So you can watch this output here. This is the drive speed output. So now if I using this control panel, okay, enable the drive, and we can see this command. And now if I select this jog, if I push this button, the forward, so we will see the output is doing something here, right? And click the backward, so we will see this simulated drive, the servo drive system is working. So if I click this linear axis mechanic, and if I click this 1, 2, 3 to show this result, again, if I push this forward, so we'll see the motor deliver a -6 Nm to the load system. If I click this forward, so it delivering the torque value 6 to the load system. So that means this simulated motor and the load also working. Okay. So now This is the panel testing system. So in the real case, if we are using the real drive system, so basically this is the essential step to verify the drive, to verify if the drive can be operated briefly. Also, we can use the forward and backward to validate the mechanical direction, and also have a quick view if the drive has an error. So now everything is running properly. Okay, so till this step, basically this is the brief procedure to set up one simulated servo system and connect it with the TIA Portal project. So the TO is a very typical TO. So behind is a Dynamics S120 drive, right? All the configuration for here, for TIA Portal side, is a very typical technology object connection with one server drive system. And the only difference is now we are using this simulated the drive system. And the next big step, we will basically using this application to show the oscillation cancellation reduction function. Okay, let's start this section now. Okay, before we start this section, let's go back to this application, this ID number. And I highly recommend you can review this manual. This manual explains the basic idea and the operation for this feature, the load oscillation suspension. Okay, and now let me show how can we implement this, which is very simple. So if we go to this watch list, I'm using this linear axis here. You will find one important variable that I named this VibX, this configuration, this enable. So default, the system is not enabled. That means this is your basically typical case without using this feature. But once you turn it on, turn this enable to true, this oscillation cancellation will be enabled. So where the function behind? So from here, we can click this cross-reference and see where it goes. This cross-reference. As we can see here, this function block FB2, this VibX enable filter is very important. So this function block here, enable filter, this is the key feature to run the oscillation cancellation function. So if we double click here, this function block, we will see a bunch of code inside. So totally it has around 400 lines code inside. We do not need to care about the detail inside. The only thing we need to enable this function is using this enable. Once it turns on, then it enables this access to run this feature. And the reason why when we turn it on, it can work on this axis, that's because for this linear axis, this is the TO axis here. This linear axis is dB8. So we are connecting here. This allows, once we turn it on, it will work on this TO here. In the meantime, we will connect to this output here, 340 and 352. This is this access output. Those hardware address, we can go back to the hardware configuration at the drive side. If we go to the drive side, so we can see here, the output they are at here. So you need to connect this QD address to the function block. Okay, so this function block joined this oscillation feature with this access TO. Okay, and this example includes this everything, so it's saving us time. So you can digest more details. Okay, to practice this feature, so we can go to this watch list, this linear axis here, and here we can enable this axis and trigger this positioning control. This positioning control is a relative control. Every time when we trigger this axis, so it will run the target distance it try to run. In the meantime, let's check out one KV parameter from this linear axis. So if we double click this technology object, and then let's go to the control loop here. So default, this gain was 0. So if we are using the gain closed loop as a 0, definitely your closed loop will show very soft, and this testing will not work. So if we go back to the rotary axis to test this application, so this rotary axis was set like a 50. That's why in this example video, it shows it was using the rotary axis to do this simulation. So here I will set this closed loop, this control closed loop to 50. Okay, set a little bit higher. Okay, and now I will save and compile and download. All right, now I'm gonna go online, and then let me open the monitor list for the linear axis and transfer the parameter. This time I will travel 20 distance and 20 velocity. Okay. And now if I trigger this drive, so the drive will travel to the 20. Okay, no problem. So this is do a very brief test. And if we go to this commissioning of this linear axis TO, so we will see this drive enabled. Okay, now the drive is prepared, is ready. And if we go to the trace, open the relative, this linear axis. Okay, this is the configuration, the same as before. And now let's download this configuration. And let's turn on, active this trace. It's waiting for me, this trigger. Okay, let's trigger. So firstly, I will run without the VibX configuration, disable this feature. Okay. And let's see this torque. So we will turn off all of them first and active this 2 position. Okay, this is the motor position, and this is the load position encoder. And I will also turn on the torque. So we will see the torque. This oscillation also caused by the gain parameter. This is the 50, the gain, the closed loop gain parameter. It's basically high. And if we use the same group for this positioning, so we can compare. Okay, as we can see, this is the oscillation here. So currently, we haven't enabled this oscillation yet. Okay, so we will see this vibration basically plus and minus 0.5, this encoder value. Okay, and the torque oscillating between the 4 and minus 4. Okay, and let's see this over picture again. Okay, and now let me turn off the drive first. And now we can prepare to turn on this VibX configuration. And before we enable this feature, let's check out this frequency. There's one frequency filter configuration, the value at here. And the reason why I set 10.3 at here, that's because if we go back to the SIMIT software, and from this load simulation here, if I right click this 2-mass system, and based on the parameter I set here, this is the motor and this is the load. And if we shift to the state, those values come from the calculation based on the parameters we set here. And the state's value shows my locked rotary, the motor, that frequency is 10.37. So that's why from the software, from the control, this filter area, I set 10.3. So ideally, I should set 10.37. And how can we get this frequent value in the real case? So you better review the manual from this application. Okay, this oscillation suspension system. So the basic idea, we can use the log chart to get this locked rotary, this frequent. Okay, so I set this value 10.3, and now I can turn on this axis, and I can enable this feature. And now I'm going to trace. So before that, I'm gonna turn on the trace again and start this trace again. Okay, it is working. It's waiting for me to trigger this motion. And now I will trigger this motion. Trigger. Okay, it moved to the target 20. And then let's go back to the trace. Turn off all the monitor and only turn on this 2 position. And we will see this time the position looks very perfect. And also we can see the torque. Okay, we will see this time it become very smooth. So if we zoom in this area, as we can see, the difference between this target and the actual load is basically within the 0.2 the degree. This is different. And this torque become very smooth. Okay. So to utilize this feature, you can go to this library blocks. And this is the VibX, this configuration, this program here. Also, for this SloshFrequency, this is useful if you are controlling a tank, and in the tank you have water. So when you stop this tank, maybe the water will vibrate back and forth. So this SloshFrequency will calculate this application. Alright, this is the topic for today. I know this is a long video, but I really like to show this whole procedure. So this is the process to set up the SIMIT, this is Siemens simulation platform, and the TI Portal version 17, this software. So I was using this drive system S120, this is server drive, and the motor and the simulated load to practice this whole procedure. And also I'm using this VibX, this configuration as a background. I utilize this example program so we can get started with this SIMIT, the Siemens simulation platform, and the TI Portal software much easier, especially for this motion control, this server drive simulation. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.